Bear with me for a second here. Okay. So we left off last time talking about inheritance, of course, we ended on looking at abstract classes and interfaces. And you kind of explored that a little bit in your labs yesterday, where you had something that looked like this, right? You had an employee payroll system where you had an employee here, and then there are two types of employees. There was an hourly employee and a salaried employee, and the way that you calculated their pay was slightly different, right? But up here, you said you had a function that was called get net pay or something like that. And it was defined up here in the employee class because everybody would inherit that kind of behavior. Every class that is an employee would have that behavior. But at one point in your lab, you were asked, well, does it make sense to have a generic employee? Just like on Tuesday, does it make sense to have a generic bird, right? Does it make sense to have a generic bank account, right? When you don't know how to compute the actual pay for an employee, are they hourly, are they salaried, how do we actually do this? Then that was screaming out to you to make this into an abstract class. And that's a perfect use case for having an abstraction. That you can't create an employee anymore. You can only create hourly employees or salaried employees. Up here in this abstract class now, how do you calculate the net pay of a generic employee? The answer is now you don't. By making this abstract, now you can have abstract methods. And one of those abstract methods would be the get net pay. So you don't have to define what it is up here. You only have to define what it is down here. But you still want it in this inheritance hierarchy because you want every employee to have this function or this method called get net pay. Because you want to put all of your employees into one list, iterate over them to find out how much is your entire payroll, right? And that was the purpose of doing something like this. Now imagine that you have an intern that is not paid at all, right? My advice to you is if you're in an area, computer science, computer engineering, software development, whatever, there's no such thing as unpaid internships. I'm sure that there are unpaid internships out there. Do not ever take them, all right? But you will always, just to give a plug, who was it over here the other day that was doing job talks? Is it Sandhills? I don't know. Anyway, Sandhills has their internship start at $20 an hour. So they pay very well over at Sandhills. I would never work over there myself because they do require you to wear a suit or something every day. But if you buy into that culture and you like wearing a tie, then that's perfect. You get paid to wear a tie. But the idea here is that these are interfaces up here. So highest level of abstraction, this is pure abstraction up here. These are things, these are concepts. What is a person? Well, a person is just a class that has this method called getName, right? A person has a name or something like that. You also have the concept of a payable, right? We don't pay our interns, but we do pay our employees and our suppliers, because if we don't pay our suppliers, then they don't supply us, right? So this relationship up here is achieved with interfaces. Interfaces are pure abstractions. They're pure abstract classes. So one of the common questions that we always get is, when do you use one or the other, right? So when do you use an interface, abstract class, or regular class, right? We don't call them concrete classes. I'll put in here, the only way that you can refer to them is non-abstract regular classes, right? So if you don't have any state and no implementations, use an interface, right? Because that's all an interface is. It's a pure abstraction. However, when you do use an interface, keep it small. This is something that goes to the solid principles. Off the top of my head, I forget what the single responsibility principle, something, I forget what the I is. Liskos substitution principle, open-closed principle, and the D is going to be dependency inversion. So we'll talk about all those much later on next week. But one of those tells you to keep interfaces small. Because if you've got an interface like this, you don't want to have like 4 or 5 different things in this interface up here. What you want to do is you want to keep interfaces small because you are sprinkling them in, kind of like those mix-ins that we talked about last week, or on Tuesday. You want to give this object this attribute. You want to give it this functionality. Well, if you give it this one piece of functionality, but 5 other pieces come with it, then that forces you to have those 5 other pieces whether you need them or not. Keeping interfaces small means that it's more flexible. In fact, one of the use cases for interfaces is that it doesn't lock you into that inheritance hierarchy. Interfaces are more flexible because they don't lock you into a hierarchy. Right? I fixed myself. This morning I was doing hierarchy with EI the entire time. I couldn't get out of the bad habit. Let's go back to, let's see, what did I want? The collections diagram here. Right. Let's go back to this diagram that I showed you briefly on Tuesday. All of these up here are interfaces, and in fact, if you look them up, the vast majority of them only have 1 or 2 methods. In fact, some of them don't even have methods at all. Random access is just a property, right? What among here has random access? The array list. Why would you say that an array list has random access? Yeah. Because it's supported by an array, right? There's an array under the hood here. So if you want to jump to the ith element, that's just a memory offset. That's what random access is. Right? So jumping to the 50th element is free. That's not free in a linked list. Jumping to an ordered element means that you have to start at the front node and then work your way through until you get to that. So if you've got 10 billion elements here and you want to get to the one in the middle, you're doing 5 billion operations to get there. Whereas with random access, then you don't have that problem. But this doesn't actually define any methods. It just says that this it's cheap to jump to a certain location with this object right here. This one does not have random access, and so it's telling you, it's giving you a property that it's not cheap to do that. We'll look at that later on with list data structures. What if we had locked that into a hierarchy? What if this wasn't an interface? What if we said that all collections have random access? Is that true of sets? There's not even a concept of ordering. There's no first element, last element, second element, etc. So by having these kind of interfaces, it means that you can magically give these things the properties or the functionality that you want without having to lock you into this hierarchy. This hierarchy is locked. You can't get out of that. You have inheritance, right? Yeah.
So interfaces are almost a way of doing multiple inheritance.
That's another use case. We'll talk about that in a little bit here, but interfaces are also more flexible because a class can implement multiple interfaces. Just like this over here. The hash tree set here is a navigable set, it's a sorted set, it's also serializable, all these things are serializable, and it's also clonable, right? So you can do all 4 of those things by virtue of it implementing the interface. Implementing an interface just simply means if you implement this interface, you have to have this method over here. You have to be iterable or something like that, or you have to be navigable, whatever that means. And whatever that means, it means that that you define a function that this thing has. It's the actual class's responsibility to implement that function. That's why we use the keyword implements. It implements whatever functions that this thing up here says it should have down here. You can do as many as you want. You can only extend from one class, right? You can only inherit from one class. Because in Java, some languages do allow you to do multiple inheritance, and we'll talk about that as a pitfall here in a second, okay? Let me restore this. All right. So, well, if you do have some state, and some functionality, maybe an abstract class is what you want. But you have to ask yourself 2 questions here. Do you want to disallow users, in other words, programmers, from instantiating your class, right? Yes, then yes, you do. Then yes, you may want an abstract class. There are other ways of preventing people from instantiating your classes. For example, local date. Local date, they didn't make it an abstract class. They just made it so that all the constructors were private. But the way that they control creation of those objects is through static factory methods. But this, if you want to absolutely ensure that nobody can ever create an instance of your class, like for example, an employee, there's no such thing as an actual employee. There's only hourly employees and salaried employees. So we can make this into an abstract class, and now nobody can create one of those things. Right? And that would be a use of an abstract class. Right? Do you have some implementations, but others are too generic, in other words, abstract, to implement? Then you probably want an abstract class, right? So that you can have some abstract methods. Right? Otherwise, if you have a fully defined object, right, that is all state, all methods, then make a non-abstract class. Right? So it's more design. And by the way, there's more than one way of doing this stuff. In fact, you should whiteboard it, right? Write down all the classes that you've got so far and say, well, this is the relationship between them, and we could make this an abstract class, or we can make it an interface, or you know what, this has maybe you could have a whole hierarchy like the collections hierarchy right here. You could define a whole bunch of interfaces, a whole bunch of abstract classes, and then a whole bunch of non-abstract classes. You could go way overboard if you really wanted to, but I would say Yagni. Remember what Yagni is. What is it? You ain't gonna need it. You're probably not gonna need it, right? All right, so you always have this back and forth with design, right? Keep it simple, but keep it only as simple until you know it's hamstringing you, and then make it a little bit more complicated. Okay. All right. Let's see. Pitfalls of inheritance. Inheritance pitfalls. So as you just asked, some languages do support multiple inheritance. Right. For example, C++. I'll put that in, but not Java. For example, you could have an animal class, a dog class, and a cat class. Right? What kind of relationship would you derive from that? You start asking yourself questions. Is a dog an animal? Yeah, okay. So then you might make it a subclass. A dog is an animal. Is a cat an animal? Yeah, so you might make that a subclass as well. Is an animal a cat? No more than a ostrich is. No more than a bird isn't necessarily an ostrich, right? All right, so there's a nice little inheritance right there, and that's good. What if you did multiple inheritance though? What if you inherited from both a dog and a cat? What do you have now? From both a dog and a cat. What would you be? You'd be maybe it's too old. Cat dog, right? And what is a cat dog? An abomination. Good. Cat dog. There we go. Right. So maybe it's some cartoon freak or what. Whatever. But you have a problem here with inheritance. What if up here we've got a talk method? And down here the dog class was overridden so that the talk method actually printed out, what does the dog say? Bark. And, bork. And A cat says, meow. What does the cat dog say? Bark? Meow? Okay, whatever that was. I don't know how to put that into words. Right? This morning I said kill me, but so there's the problem, and it's called the diamond problem. Right? Multiple inheritance leads to the diamond problem. Which class does the subclass inherit from? Right. So in programming languages that support this, C++, you have to explicitly say which class each method is derived from. In other words, you essentially have to write code to say, I'm inheriting the dog's bark method, or I'm inheriting the cat's meow method, or you have to provide your own now new custom code to say whatever that was before, right? So in other words, you're going to have to write code anyway. So if you're going to do that, then why have multiple inheritance to begin with? Because if you have to write code anyway, you're kind of defeating the purpose of inheritance of not having to rewrite code, right? Java does not support multiple inheritance. However, Java does allow you to implement multiple interfaces. Why is that not a problem? I can pull from interface A and interface B and interface C. Interface A and interface B, suppose that they both have this foo method. Am I really inheriting any actual behavior from those interfaces? No, because they are purely abstract classes. There is no implementation up here. It is just the function signature. It means down here I have to implement a foo method, whatever, but I'm not actually inheriting the behavior from either one of those classes. Right? And that's why it's not a problem, because it's just pure abstraction. Right? Java 8 did, unfortunately, introduce default methods in interfaces, which kind of breaks this entire thing. Don't worry about it. It was a mistake. In my opinion, it was a mistake for them to have done this. But my opinion doesn't matter with the Java people because they don't even know who I am. But they did introduce this. It does throw a little bit of a pickle into this idea, but so be it. Whatever. All right. So questions on multiple inheritance? Again, if you're just inheriting from multiple interfaces, you're just inheriting the method signature, and there's no conflict at all, because if these were interfaces, you wouldn't have bark and meow. You would have talk, and you don't know what it says. You don't know what it says, but you have to say something down here. Right? So you'd have to implement it. Okay. Another problem is the yo-yo anti-pattern. Right? So deep inheritance hierarchies can be very complex. So say that you have a really, really deep inheritance hierarchy. Now this one is getting to be pretty deep, but let's say that it was 3 or 4 times as deep. In other words, you had, instead of a 1, 2, 3, 4, 5 classes deep, say that you were 20 classes deep. Right? Now you need to make sense of this design. So you start thinking, well, which one do I actually want here? Okay, I want this one, but now it's a little bit more general. So I go up the hierarchy until I hit, okay, well that's too general. So you go down the hierarchy, and oh, by the way, what methods does it provide, and where did it inherit that one thing? You have to go up 10 more classes to find what is the base implementation. Okay, now it overrides here, and you go down, and you go up, and you go down, and you go up and down. What are you doing with your head? Looking at this deep inheritance hierarchy to figure everything out. You're yo-yoing, like you're watching a yo-yo go up and down, right? Now, you don't watch the yo-yo go up and down when you watch a yo-yo, right? But that's why we call it the yo-yo anti-pattern. But that deep inheritance hierarchies can be way overly complex. Instead, in general, prefer to have shallow hierarchies, right? If you are, I did it again. If you are having a really, really deep inheritance hierarchy, think about how you can flatten that out, or maybe you can collapse it somehow. For example, instead you could prefer composition over inheritance. Right? So if you've got a really deep hierarchy because you wanted to inherit this thing and this thing and this thing, well, maybe it's okay if you just have a class that owned an instance of one of those three things. It also goes to the fact that you should really be careful about putting things into a hierarchy and locking them into a hierarchy because they might not necessarily be compatible. For example, when we looked at our, oops, that's over here. Where is it? We did this one, certificate of deposit and person, right? In the person class, in the certificate of deposit class, bank account. Where's the bank account? That's what I want, right? We use composition to denote an owner because an account was not an owner was not an account. We also preferred to have an address in a different class, and then a person owned an address instead of putting it in this hierarchy, right? Because it doesn't make sense. An address is not a person, and a person is not an address. Separate those out and prefer a shallow hierarchy instead, right? A collection of objects rather than locking it into this really deep hierarchy, okay? So prefer composition over inheritance, and that'll avoid the yo-yo anti-pattern. Finally, the rectangle problem. Right? Oh, no. I should have rolled it back. I didn't have time to roll it back, so ignore me for 1 second. Where's my rectangle? There we go, shape, square. All right. So, yeah, okay, I'll just show it to you. So I've got a shape, a rectangle, and a square, right? I'll start with the shape. First of all, why did I make this abstract?
Because both squares and circles are shapes.
Okay, they are types of, what's a shape? Is there such a thing? There's no concrete idea of a shape. It's an abstract idea. It's a category of other ideas. So I made it abstract. Now, what I put into this shape is you can get the area. So if it were a circle, then it would be pi r squared. If it's a rectangle, it'll be width times height. If it's a square, then it'll be side squared, right? Because equal sides everywhere, right? But I also wanted to maybe be able to reset the width. So now, before I go on to square and rectangle, tell me, is a rectangle a square? Okay, sometimes. Or then go the opposite. Is a square a rectangle? Yes. All right, so the opposite way, probably not. So what I did is I made a rectangle, extend shape because it's a shape, and then I made a square into a extend a rectangle. So what does that look like? I don't know if I have an eraser or not. Okay. Oh, really ugly. All right, so shape. Oh, okay, too late now. Rectangle and square. That's the hierarchy I've defined here, okay? Now, you said sometimes. A square is always a rectangle. Is a rectangle a square? The answer that I heard was sometimes. What happens when that sometimes screws things up? Let's go to the demo here. All right. Ignore this for a second. All right. I create a shape and instantiate it as a square. And this constructor right here, what does it do? Well, it calls a super constructor on the width so that the width and the height are the same. Okay? So it's still a square. At this point, it's a square. In fact, I've set a breakpoint here. I can prove it to you. Let's go ahead and go into the debugger. And when I look at the height is 10 and the width is 10. So what should the area be? 100, right? And if I printed it out at that point, you could see that. But then the very next line, what do? I set the width to 20. Okay. Let's go ahead and step over that. Now, before I print out the area here, is this a square anymore? 10 by 20? Nope. But it is a square, right? Semantically, code-wise, it's a square, but semantically, it's no longer a square because it's 10 by 20 now. Right? And that's because I had a really poorly designed hierarchy. It's a couple of mistakes working together. Me locking this into a hierarchy, and then also having a mutator function here that actually changed a property to give it the semantics of another class. Right? Changing a square so that it was no longer a square, that it was just a rectangle. Right? Hierarchically, within this hierarchy, it's still true, but semantically, it's no longer true because it's no longer square. So this is called the rectangle problem, right? If you have a flawed inheritance hierarchy and or mutator functions, in other words, setters that can semantically change what an object is, then you may run into the rectangle problem. Code-wise, the object is still of the subclass, but its properties redefine what it is. In other words, what it is being its semantics. Its semantics. Right? Its meaning. Right? You're changing its meaning even though you're locked into this inheritance hierarchy here. You can treat a subclass like a superclass, but you shouldn't be able to change it so that it is a superclass. Right? This is kind of a violation of the L of solid, which is the Liskov substitution principle, meaning that if you've got any instance of a class, you can change, or you can replace it with a subclass instance of a subclass of it without affecting the meaning, the semantics, or the behavior in some cases. Okay, that's the rectangle problem, and the solution, of course, is to make sure your design is well thought out, and not necessarily future-proof, but well thought out because it is very difficult to change a hierarchy later. Right? It is, in fact, it's nearly impossible. Java, the collections library, it has not changed. The hierarchy that they defined over here was well designed, and it has not changed. Thankfully, it has not changed, because if you ever go and change this stuff, you forward break all Java code going forward. And Java it takes great pains to make sure that it is backwards compatible. If you go and muck with this hierarchy, that means that it's incompatible with all the code before it, right? Potentially. Okay? All right, inheritance questions? Otherwise, we've got some miscellaneous stuff to cover at the end, but now we'll move on to the fourth pillar, polymorphism. And just as I think I said that the encapsulation and abstraction are kind of like the M.C. Escher hand drawing the other hand, yin-yang kind of thing. In a way, inheritance and polymorphism are similar. Because when you talk about polymorphism, generally you mean subtype polymorphism, which is the default type of polymorphism. But before we do that, we need to define what it actually is. So poly is what for you? Is it Greek? Greek speakers? Okay, many. Right. Morph is change, noun-wise, form. All right. So in other words, many forms. Polymorph or polymorphism is equal having many forms. All right, any biology folks? Have you ever heard of polymorphism in the context of biology? Or polymorphs or phenotypes? The different species have different phenotypes, right? Like you can have tigers, and one of them is striped and one of them is polka dot or whatever, spotted, there we go. And those are different phenotypes. In other words, they're the same form, but just slightly different things. And in the context of code, polymorphism is the ability for one variable, class, or piece or method to have multiple forms at different points in a program. Right? And you can actually see kind of proto-polymorphism in old programming languages like C. For example, how do you sort? In C, what function did we use in C to sort? Qsort. In other words, we had one function that sorted anything, one function that had multiple forms. That function was able to sort an array of integers. That function was able to sort an array of doubles. It was able to sort an array of whatever, transactions. How did it work?
By looking at the input type.
Well, what were the signature? What's Qsort's signature? What is it? It takes an array of what? Of anything. And how did C achieve anything? Constant void pointers, right? It took anything and then made it this generic thing, this void pointer. Right? In Java, you can kind of do the same thing. Any object or any class is an object because you inherit from these objects. Those are called raw types, and it's kind of it's bad to do that. Right? Instead, you want to use true polymorphism because this is an object-oriented programming language, right? But the idea here is that you have one function that can operate on any type, right? Provided you give it the appropriate what was the comparator. Right? In Java, you have various different types of polymorphism. You can write a variable or method or even a class to apply to more than one type. Right? Here's the classic example. Right? The classic example here is going to be a collections or collections. Right? And I'll go into code mode here. Right? A list of elements, numbers, let's say, equals new array list. Right? I'll do it like this. In fact, let me go over to Eclipse here. Can't remember your name, Eclipse. There we go. And it's complaining because these have not been imported yet, but let me go ahead and do it. Now, I've never shown you this way of creating a list before, and I'm telling you, never do something like this. This is the old school way prior to Java 4 of doing it. Right? What is that a list of? All right. It could be a list. I called it numbers, but I can add a number. Sure. Numbers.add 10. I can also add strings. I can also add, I don't know, a new square. There we go. And it'll allow me to do that. Why? What is it a list of? Yeah. Of objects, right? So without parameterization, then a list can contain any type of variable. Right? Well, that's kind of bad because if we have an assumption that if I put stuff in, I pull stuff out, and I want to add them all up, if I have an assumption that these are numbers, well, my assumption is no longer valid, is it? Right? So let me go ahead and change this to a list of integers. Right? And I can't use numbers anymore, so I'll call it foo, new array list. And now, numbers.add 10. This will work. Numbers.add, or numbers, foo, foo.add. If I try to add ten, a string, it's not going to let me do that. Why? Because I said that this is a list of only integers. Now, the polymorphism here is under the hood. It's in the list class. The list class has been made into a polymorphic class that you can create a list and parameterize it on integers so that that list becomes a list of integers. You can parameterize a list so that it's something else, say, I don't know, strings. Oops, I'm struggling. String bar And now, just the opposite happens. This is, oops, bar. There we go. There. Now you can add strings, but you can't add integers anymore. Right? That's the polymorphic behavior. That this, I didn't have 50 different array lists. Right? An array list for integers, an array list for doubles, an array list for strings. Instead, I had one array list, and by the way, I should be doing it correctly over here. There we go, and there we go. Oops, there. That's the proper way of doing it. The polymorphic behavior is you can write one class or one method or one variable, and it can be anything that you want at various different points in the program. Right? So that you don't have to rewrite code over and over and over again. You can write one version of the list or an array list, and you can have it apply to anything in the future. Right? That's one type of polymorphism. That's called parameterized polymorphism. Right? Collections illustrate parameterized polymorphism, right? That you can create a class, or I'll just keep it to classes. You can create a class that can be parameterized to any type. Right? Using something like this, the following is a raw type, right? That only apply, that parameterizes it to objects. Right? Do not do this. Right? If you're in Java 4 or prior to that, then yeah, go ahead and do that. Right? But that's parameterized polymorphism. In my opinion, that's the most powerful form of polymorphism, modern polymorphism, so that you don't have to write 50 different array list implementations. Another one is subtype polymorphism. Right? You can treat any subclass, or you can refer to any subclass as its superclass. For example, if I've got a savings account, S is equal to new savings account, and blah, blah, blah. I don't know what's there. But you can also refer to S as its superclass. You can say a bank account, B is equal to S. Right? Remember, what kind of coercion was that? We had that triangle diagram, and treating a subclass as its superclass was one. Treating a superclass as its subclass, that was not necessarily safe. That was a contravariant coercion. Treating a sibling as a sibling, treating an ostrich as a robin, or a savings account as a checking account, that's invariant and that's never safe. But it's okay to take a subclass like this savings account and treat it as its superclass. That's covariance, right? This is called covariance. Right? You can treat a subclass as its superclass. Now, why would you want to do this? I briefly showed it last time. Let me go ahead and get rid of all of this, or at least comment this out. That if you want to create, let's see, I thought I had another demo somewhere. OP, is this the demo? Nope. No other, there should be like a demo H somewhere. Does anybody see it? Maybe I got rid of it. No. Okay, I got rid of it. But anyway, so if I've got a savings account, or a list of savings accounts, right? My savings accounts is equal to new array list. I want to know how much I'm my net worth, basically, right? And so I've got savings accounts and I've got checking accounts. Checking accounts. There we go. I want to know how much I'm worth, right? My net worth. So I want to sum them all up. For savings account S in my savings accounts, then total plus equals S dot, we get balance. There we go. And I need a total here, double total, started out at 0. Add those all up, copy, paste. That should be your first hint that I'm doing something wrong, right? In my checking accounts, and All I'm doing is changing. All I'm doing is what? Changing what? Same exact loop, right? Both of them have a get balance method. And I'm just summing them all up. What's the difference between these two loops? Other than the variable name. I could use the same variable name. S and S. There. Now what's the difference? The type. One's a savings account, one's a checking account. How could I have done this differently so that I didn't have to double up on my code? And in fact, think future-proof this. What if I have a bunch of money market accounts or a bunch of certificate of deposit accounts? Or 5 years from now, somebody else inherits this code and we establish a new kind of 2025 savings account or something, right? And they need to create a new class. Everywhere I do my business logic of summing things up, of persisting to the database, basically everywhere that I have a reference to a savings account, if I take this route, then I need to touch every single piece of the code and add another loop or add another if condition. If the account is of type savings account, do this one thing. If the account is of type checking account, do this other thing. If, else if, else if, else if, you've got this huge giant if, else if conditions based on every single possibility. Right? But it's all the same. Get balance, get balance. What could I have done instead? Have a banking account. Bank account? Oh, yeah, bank account. All right. My accounts, right, is equal to new array list of bank accounts. Right. Now I don't need all this code, and I've future-proofed it. Any type of new bank account that you introduce, you don't need to change this code at all. All I need to do is iterate over all bank accounts in my account. And I don't have any here, by the way, but it's okay. Oh, I got rid of total. Where's the total? There we go. And uncomment that. Oops. Whoa. And A. There. That is very succinct code. And it's all because of subtype polymorphism. A savings account is a bank account. A checking account is a bank account. They both have this get balance method inherited from their parent. So all I need to do is treat them the same. If all I care about is balances, then I can put them into one generic list with bank accounts. I can put in bank accounts. I can put in checking accounts, savings accounts, money market accounts, CD accounts, any accounts that you create in the future, I can put it into this one collection and not have to change a single line of this code over here. Right? So subtype polymorphism. It allows you to utilize a common interface and treat all subtypes the same as its supertype. Right? Reduces code, future-proofs your code if new subtypes are introduced later on. Right? So that's subtype polymorphism. That's why it's really, really powerful as long as you designed your hierarchy correctly. Okay. Two other types of polymorphism that we'll talk about today, and then we'll go ahead and end it there. One is function overloading. Right. So recall in C, I'll go ahead and go like this. In C, there are several functions to compute the absolute value. Right. What were some of them? Do you remember? Fabs. Labs. Labs. What else? Labs. And also abs. What is abs? That's for integers, right? Etc. In fact, I think there are actually more depending on your libraries. But function overloading is the ability to define multiple functions with the same name, but different parameters. Example, how do we achieve this labs, fabs, abs? How do we solve this in Java? Java math. Are there absolute value functions in the math library? How many? 4. How do they differ? They all have the same name though. ABS, 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 abs. Same name, but different parameters. One of them takes a double, one of them takes a float, one of them takes an integer, and one of them takes a long. Right? So in other words, or let's say math.abs. There are 4 methods with the same name, but different parameter types. Right? So as long as a function differs in the arity, that is the number of or type of parameters, the compiler can deduce which one you are calling. Right? For example, with absolute value, if I in Java, if I have a double x is equal to negative 3.14, and I call math.abs on x, then which one is it probably calling? The compilers are dumb, but they're good enough to figure this out. Which one of these am I actually calling? The first one, right? The one that takes a double. If I pass in an integer instead, int y is equal to negative 3, math.abs on y, which one am I calling now? The third one. Right? In other words, it can look at the type that you're passing it, and it can say, okay, well, you're passing it an integer. Oh, you probably meant this one over here. And in fact, my IDE can figure that out too. I'm passing it an integer. It's going to the one with an integer. If you're passing it a double, it's going to the one that takes a double. Right? Now, the way that this works is called static dispatch. The compiler is able to tell which one to call using static dispatch. We've already heard a term very similar to that, dynamic dispatch. Do you remember what that referred to? All right, then it's my, I'm once again going to my screwed up diagram that I thought would kill, but it didn't. All right, that's dynamic dispatch. When you create 2 birds in memory, right, and you refer to them both as birds, then this is all the information you have at runtime, that it's a bird. How does it move? When you call the move method, does it fly or does it walk? So the way that that works is when you create a robin, you're referring to it as a bird, and it only has this move method. This is a virtual table that has a reference to the appropriate method that you created when you created the class. And again, this one should be from move, that refers to walk. That's dynamic dispatch. Dynamic dispatch happens at runtime. We call this static dispatch because it happens at compile time. Right? We heard those terms before, dynamic testing and static testing, or static analysis and dynamic analysis. Right? Static always it has nothing to do with the keyword static in the context of Java. It just simply means it's something that happens before or during compilation. Right? Dynamic means that it happens when the program is actually running, so after it's been compiled and it's running. Right? And same with dispatching. Static dispatch, the compiler can figure it out at compile time, and it doesn't need to do anything special at runtime. Dynamic dispatch is, it doesn't know at compile time that this bird is referring to a robin or an ostrich, so it has to rely on the virtual tables and dynamic dispatch to do so. That's function overloading, very, very convenient, because otherwise you have to go to old school C style of coming up with a new name for every single one. Right? All right, and then you have to remember, one of the common issues that we see in CS1 is people always using abs, 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 and then they're losing precision because negative 3.5 the absolute value of that should be positive 3.5, but they use abs and they get 3, right, because of truncation. And C is more than happy to do that for you, but overloading solves that problem, right, because the compilers are smarter. Right? All right, there's another type of overloading, operator overloading. Right? Operator overloading is simply just an operator may have more than one meaning depending on the context. Right? Just like polymorphism, many forms, you can take an operator and overload it so that it has different meanings in different contexts. In Java, for example, what is a string plus a string? What does it mean? Concatenation. If it's ever too small, low, let me know. I can go lower over here. It'll just give me some carpal. All right. String plus, or no, easier one. Int plus int. What does that mean in Java? Addition. What does string plus int mean? Concatenation. All right. What about in PHP? You remember? If I've got a string plus a string, you can do this, but what does it mean? Yeah, what do we call that? Juggle both and add, right? And perform addition. Right? Instead, what did you need for concatenation? String dot string means concatenation. In other words, PHP does not have operator overloading. Java does have operator overloading. The plus means different things in different contexts. And thankfully, that's the limit of operator overloading. In some languages, like C++, anything can be overloaded. Any operator can be overloaded. Oh, which? Ooh, okay. So you consider that an operator? Okay, all right, I'll buy it. All right. So most, fine. Most operators can be overloaded, right? For example, plus. You could change plus to mean minus. You could change multiplication to always result in a random number. Right?
Change the bit shift operator to output to standard out.
Oh, yeah. Oh, it is. It already is. You could redefine it to be something else entirely. But some things it makes sense in Java. Oh yeah, that's really convenient. Plus is really convenient. But like anything, Yagni, you can go overboard. You can over-engineer stuff. Now you can start out, pretty reasonably. Set plus a set. What does that mean? What would you interpret that to mean? If I had a Java set and I put plus a Java set, sure.
And the result of one set to the other.
Oh, is there a notion of a beginning and an end though with a set?
I'm going to say no.
Okay. So what is a set plus a set? It's combined. How would you combine it?
Into a new set that contains all the contents of the previous.
And that is called a. Oh, you get 235 right now, aren't you? Are you to set theory yet in 235? Union, right? Okay, that's reasonable. List plus a list. Now what would you interpret that as?
Appending list G.
Appending. Okay. Or maybe it's also reasonable to say that that's concatenation as well, or union, or maybe something else. For example, if it's a list of numbers, what would you do? That is there 5 numbers and 5 numbers plus would be vectorized addition, right? Where you component-wise addition, right? It could be like that. Yeah. Union? Oh no, union. Set theory is way older than.
Really?
Oh yeah, set theory goes back to why can't I remember the name? The axiomatic set theory is due to not Zermelo-Fraenkel set theory. So Zermelo-Fraenkel, and even before that, it would have been Cantor, and even before that, you had the notion of sets. So I'm sure that the ancient Greeks had stuff like that, right? So union is just taking these two things and adding them together. Taking a union of sets, A, B, C, C, D, E. The union is going to be A, B, C, D, E. Taking out the duplicates for sets. Right? And then there's also intersection, right? The actual modern notation, I think, is due to Russell and Whitehead, Mathematica, Principia Mathematica, or something like that, like 100 years ago or so. Old stuff, yeah, right? Here's another one, though. So, in other words, there are multiple interpretations, multiple reasonable interpretations here. What is time plus time? But what if both of the times are in the past? Oh, I guess also later.
Oh, like if you have,
Actually, no. If it was represented by a number and it was a negative number way in the past, then a negative plus a negative is going to be really, really far in the past. So either later or earlier, depending on the numbers. What is 3 o'clock plus 5 o'clock? You could interpret that as 8 o'clock, but that's a time plus a duration afterwards, right? So, whoa, way too many interpretations.
I mean, you could interpret it as the number of seconds, like since the start of the Unix epoch.
Well, yeah, but then if it's prior to the epoch, then it's going to be negative plus a negative, and now it's even further back in time, right? So there's no good interpretation here, right? So in general, you want to avoid operator overloading, right? Why? It's far too ambiguous, right? That there are many, many interpretations, and at the end of the day, you have to write code to implement the operator overloading anyway, right? And if you have to write code, put it into a function. If you have a function, give it a good name. Right? If you have a name, a good name, you have a well-defined explanation. It's no longer ambiguous, right? And this is how the date-time library works. You can define durations, times, etc., and with a time, add 5 seconds, right? That add, subtract, right? Those have defined names rather than just a plus and a minus that might have many different interpretations. Yeah.
Operator overloading, you could, for example, implement your own string class instead of relying on compiler magic to do that for you.
You could, but then why?
I don't know,
You're reinventing the wheel at that point, right?
maybe you're working in like a constrained environment where the standard library is not available.
Then you're in, yeah. Then you're in the C world, and you don't really have any objects or any of this nice fancy stuff anyway. I imagine.
A C world?
It's like the world of C, embedded stuff, where you don't have all this stuff. The more important thing is to have readable code because you want maintainable code. If you are in a strict environment where you only have 34K to work with or 32K to work with or something like that, and you can't load in a nice string library, then yeah, you're going to have to use some low-level stuff. But that's exactly why the string class in Java is final. You can't subclass it because they don't want you to, because strings have a well-defined meaning and compiler magic to achieve this kind of stuff. So what you might have been referring to is that when you do a concatenation, like string s is equal to hello plus b, and string b is equal to world. Right? Now, the way that this gets concatenated and created, it's all opaque to you. You don't have to worry about it because of operator overloading. Right? What actually happens under the hood is that the compiler is changing your code. It's changing it to look something like this. String builder changes to something like this. String s is equal to a new string builder with dot append hello dot append b dot toString. Right? So the compiler is changing your code right here, which is a plus, into this long string of actual method calls. So the compiled Java code, there are several levels of compilation, but initially it gets compiled into something where there is no operator overloading. that it's a different interpretation. So then that's what gets compiled to Java bytecode. In fact, you can decompile Java if you want to. And if you decompile Java, some of these things become apparent. I'm not sure, I haven't decompiled a Java file in a long time, but you can do it pretty easy. You can see that your code probably looks like something like this. You start out with code that looks like this. You compile it to Java bytecode. You decompile it. You don't get the original here. You get something that looks more like this, because it's performing magic. It's doing some behind the scenes replacement of your code so that it doesn't have to have plus. Yeah.
When obfuscation comes into play with people's code after they put it out in the market and stuff, kind of I don't understand the point of that if you can just go back into the bytecode and come back with basically most source material and then you just go back and
Oh, compiling is not obfuscation.
well yeah.
I mean, it's some obfuscation, but that's more of a fact of that the Java bytecode is very well defined. So, I mean, it's a public standard on what Java gets compiled to Java bytecode, that entire process. And if that entire process is understood, then the reversal is well understood too, right? Even GCC, you can decompile it to a point. You can definitely decompile it into machine code, right? You can decompile, just having binary is no protection against somebody not being able to reverse engineer. And reverse engineering, that is absolutely protected, and thank God it is, right? Because without the right to reverse engineering, to reverse engineer systems, we wouldn't have the world of computers that we do today. People had to reverse engineer IBM and win fights against IBM in order to have personal computers, right? So information should be free. The only way that you can protect your code, if that's what you're trying to do, is through licensing. And then the only way to enforce your licensing is to get a lawyer. And now you're probably spending more money on the lawyer than you're ever going to win in court, especially if you're fighting a big guy.
Oh, yeah.
So fight the big guy by simply just open sourcing your stuff and then having a better product or whatever, right? So in general, you want to avoid operator overloading simply because it's ambiguous. It doesn't really buy you anything that a good function with a nice, good, well-defined explanation provides. All right, and that's why Java doesn't do it. Java only allows you to do, it has built-in overloading, but only in the context of strings. C++, it's the Wild West. You can do whatever you want, whenever you want. In fact, the big three, I think, of operator overloading are a constructor, copy constructor, and assignment operator. And you overload the assignment operator so that you can get this. It's all boilerplate that you have to do in C++. So there's a lot of stuff that you have to do in C++, and it doesn't really benefit you at all, right? As far as code maintenance goes, all right? And just so I can put these here. Actually, yeah, okay, so we did PHP. What about Python? As the last thing here, I'll ask this just as trivia, Python. What is your interpretation of string plus string? Concatenation, okay. What is your interpretation of number plus number? Yeah, plus number. It's going to be addition, right? So in other words, you can use plus for concatenation in Python. What about string plus number? Now, if this were Java, of course, it'd be concatenation. If this were PHP, this would be type juggle, type juggle and addition. What is it in Python? Yeah, error, right? You cannot do it. You'd have to wrap the number in a call to str, right? That's always a gotcha for me because I don't use Python on a daily basis. So every time I see that, damn it, I forgot str. And I never remember that because I never use it consistently enough that I get into that mode of, yeah, you can't use operator overloading. So operator overloading, understand it, and know that whenever you pick up a new programming language, you have to think, what is plus? Does that only ever mean addition, or does it mean concatenation? What happens under those conditions? Because I've just shown you 4 different languages that they all do different things with the operator overloading. All right. So next week, we'll continue with a little bit more of polymorphism and then move on to SQL, right? Database stuff.